Hello everyone, welcome back to my channel. So today we are seeing about this topic screens, that is ideal and actual. So we are seeing here standard screen series, that is testing use measurement of the particle size. So this is the measurement method for any particle size. Okay. So we are seeing about the screens. It measures size and size distribution of particles between 3 and 0.0015 inch. So in this size range, we are going to measure the particle size and its distribution, how it is distributing. Is it even or is it not even in this distribution? We will be seeing that. Okay. So the testing screens are made of woven wires. These are woven wires. Okay, so these are the screens. They are like meshes. They are having openings that are square shaped. Okay, each screen is identified as meshes. See, that is openings per inch. So actual openings are smaller than those corresponding to mesh numbers. So we have different mesh numbers here. I have mentioned two of them. That is an example. That's it. 40 mesh screen, 10 mesh. So all these are, mesh numbers, but actual openings are smaller than this number. Okay. So some standard screen series are three of them are there. See, they are standard ones which we will be using. Okay. Taylor standard screen, British standard screen, ASTM standard screen. So Taylor standard screen, this is most commonly used. Okay, and ASTM means American Society for Testing and Materials. I know, I hope you all will know about this. So I have just mentioned, and one more is here. See, British standard screen. Okay, here we are seeing Taylor standard screen series. So this is based on the 200 mesh screen opening, which is established at 0.074 mm. Okay, so it is 0.074 millimeter. Okay, fine. So this is a screen, standard screen, which is having 200 mesh screen, and the opening sizes as mentioned here. Okay, so this is given as ratio of actual mesh dimension of any screen to that of the next smaller screen, which will be below that mesh. Okay, that is root 2, given as 1.414. So its value is given here. Now see, an divided by an plus 1 will be equal to 2, and the dn divided by dn plus 1 equals root 2. That means a is the area here and d represents the diameter. These are for the particles. Okay, an is the mesh number. Okay, area of the mesh number. Okay, so I have mentioned only area here, so just check it. Okay, so for closer sizing, intermediate screens are having the dimension of fourth root of 2, or see 1.189 times that of next smaller standard screens are used, but not much. So they are not commonly used, so we are just having that available in this mesh dimension. Okay, so examples are given. See here, our standard screens will be of the whole numbers like 3, 4, 6, 65, 100 and all those, but intermediate screens, they can have the fractional values also to give more closer sizing. Okay, so mechanical separations, in that we are seeing again, these are frequently needed to separate the components of a mixture into individual fractions. Why do we do mechanical separations, and what is the subject all about? We are just seeing here. It is having two ways, that is diffusional operation, mechanical separation. Diffusional thing we are seeing in mass transfer subject, and mechanical operations, it is used for solids, mostly used for solids only. Okay, so in that we are having different methods. They are like seven type of methods here. First is screening. second is filtration, third sedimentation, heavy media separation, differential settling, high tension methods, and magnetic separation. How this mechanical separation method is based? So it is based on the physical differences in size, shape, and density of the particles for heterogeneous mixtures. That is what I have mentioned. Next we are seeing, so the two types means two main methods of mechanical separation are sieve, screen, filter, membrane to pass only one component. So like we are having the screens, as you know, this is separation method. How we are doing, that is of two main types. So using the filter, screens, membranes you can do, and also the difference in the sedimentation rate of the particles as they move through the liquids or gases, that is also considered. Next is the screening, the main thing which we wanted to discuss today. So it is a method of particle separation based on size alone. Based on only particle size they are separating. So that is called screening. In most cases, screening is done on dry basis, but occasionally we can do on wet basis also. So in industries, solids are dropped and thrown on screening surface. So these are measures and screens are there. No, we will be dropping the solids on that, and only the mesh size, only fine particles or undersized particles will pass through, but oversized will not pass through. So now we are discussing about ideal screens. So these screens are separating the feed mixture. See here, without any overlapping, in a way that is smallest particle in the overflow would be just larger than the largest particle in the underflow. So you have to see this. So there is a cut diameter called DPC, denoted by DPC. Okay, it is defined here. So which makes the which marks the point of separation between the fraction. DPC is nearly equal to mesh opening of screen. This you must remember. This is like a note point. DPC is nearly equal to the mesh opening of the screen. We are having the screens, right? In that we will be having the openings. That number will be equal to our DPC. So there is nothing new in this. Ideal screens means it will be giving you the great separation of any mixture of particles, and there will be no overlapping in any ways, whether it is overflow or underflow. Okay. So here I have given the performance plots of ideal screen. Two of them are there. See in this from 0 to 1. Here we are mentioning diameter. In x-axis, y-axis we have taken cumulative fraction of particles. Okay. So two of them are there, two plots. See here, point C is the output. So what we are getting, this is the result. So this point is of separation. Fraction A has all the particles larger than DPC. So this is having particles larger than this cut diameter. So this is oversized particles. And the fraction B has the smaller particles than DPC. So these are all underflow or undersized particle. This fraction is denoting it. Okay. Next we are seeing here oversized and undersized particles which are taken and plotted separately. So we have to plot this. We are getting these values, this type of curves we will be getting. See here, this is dp, which is our equivalent diameter of particle. Then this is cut diameter, okay, dpc. So the actual screens, this is the last topic. These screens do not give sharp separation of particles. So as the name itself indicates, there is no sharp separation of particles. So overflow has appreciable content of particles smaller than desired cut diameter, and underflow has the particles larger than the cut diameter also. So this is one of the plot here I have mentioned. See, dp is here, dpc is here, they are all overlapping here. Okay, so this is undersized one, first curve. Second curve is for feed, and the third curve is for oversized particles. I hope you will understand this. So this was our today's topic. I am completing this much, and next we will be seeing a few more topics, and I will be completing this unit. Thank you.